Press. Opa. Okay. To introduce you now. Welcome to our last cryptography for this semester. I'm very happy to have Ryan Keegan from University of California in San Diego. Ryan is a fourth-year PhD student under the supervision of Nadia Heninger, and his research interests include practical cryptanalysis of real-world crypto systems, and he's particularly interested in lattice reduction. And today she is going to give a talk on fast practical lattice reduction through iterated compression. Thank you for joining us, and the screen is yours.
All right, thank you for the introduction. So yeah, this talk is about our work on fast practical lattice reduction through iterated compression. And I know there are a lot of different words in that title that may or may not be new. So to start this presentation, I'll actually go with some of the results. So for this first result, we're considering the RSA partial factorization problem, where we consider the case where we have a RSA public key n, and we know that the attacker has access to partial information about the private key p and q. So if they know some of the most significant bits of p or q, well-known result of Coppersmith has shown that knowledge of half of the bits of p or q allows you to efficiently factor n. The issue is to actually reach this bound of 1/2 the bits of p or q is actually quite difficult, and it requires a small amount of brute force and reduction of large lattices. So the previous best results for performing this attack, we took the numbers from a 2023 paper that said it would take around 470 core hours. And using our new implementation of lattice reduction, we get that down to 18 core hours. So that's a 20x improvement over the prior best. Now we have this image on the right that is labeled the profile, and I won't explain exactly what's going on right now, but throughout the course of the talk, hopefully by the end, you'll understand a little bit more about what's going on here. I guess this may be another good point to say that if there are any questions throughout this talk, feel free to ask them. I'm not able to see the chat in Zoom, so if there's a question posted there, feel free to interrupt me and ask it verbally. All right, so we have this second example here, the Gentry-Halevi FHE problem for fully homomorphic encryption.
Excuse me, may I ask a
ahead.
question, if I may do so? The visualization is on Python or on MATLAB? Which soft you used?
It's software that I wrote in Python.
In Python, okay, thank you.
Yep. Yeah, but it is all open source, and I'll go through those details at the end. All right, so for the Gentry-Halevi fully homomorphic encryption problem, we have the problem of given a ciphertext and a public key, recover that plain text. And for the Gentry-Halevi FHE problem, there are challenge public keys that were posted online in 2011. And the challenge being that if you can decrypt a ciphertext, then you have broken the system. Now, as part of this system that was proposed as a challenge in 2011, there are a few different parameter sizes. There's toy, small, medium, and large. And the toy parameter sizes were practically broken in 2015 in 24 core days using a dedicated algorithm. They scaled out the performance of their algorithm to suggest that the small parameters could be broken in 15.7 core years. Our achieved results using a new implementation solves the toy and small problem in 15 core minutes and 31 core hours respectively. So that's, I believe, around a 2,000 or 3,000 time improvement over the prior best. All right, so sort of to give an outline for the talk, we'll go through what is lattice reduction. So I will not assume any sort of prior knowledge about lattices or lattice reduction. So I'll go over a geometric intuition for lattices, and then also talk about what the profile is with respect to a lattice. And the profile is that animation that you saw earlier. Now, lattice reduction is slow, so there are a couple main candidates for how to improve it. And these different methods of improvement are sort of in conflict with one another. There's the recursive approach and the floating point based approach. And it's difficult to get both of these approaches working simultaneously. Next, we'll talk about how we attempt to merge both strategies. And we'll talk about some other recent work. And then finally, if there's time left at the end, we'll go through results. All right, so to start with the main ideas, so what is lattice reduction, or more specifically, what is a lattice? So if you've been to any sort of lattice talk before, you'll have seen this slide. It is a visual depiction of a two-dimensional lattice where we have this grid of repeating points. We have this point in the center that represents the origin, like on a coordinate plane. And you'll see that the repeating grid is quite consistent. To be a little bit more formal about it, you can represent this lattice by a set of two vectors. So we've depicted those vectors with blue arrows and given their coordinates there. And now we say that any other point in the lattice or any other vector in the lattice can be reached by taking a sum of these two vectors. So are you able to see my mouse right now? Is that showing up in the screen share?
Yes.
Okay,
Yes.
great. So for example, this point is a multiple of 3 of this vector, and this point is a multiple of 4 of this vector plus 1 of this vector to get here. So any point in the lattice is an integer linear sum of these vectors. Now that's the geometrical representation. Computationally, we don't represent every single point individually. So computationally, we just represent these vectors. And more traditionally, we just represent it as this matrix here, which is the basis matrix of the lattice. Now, the basis matrix of a lattice is not unique. So although this is the same lattice, we have slightly different vectors that generate the same set of points. So why would we care what basis representation we have, even if it's the same lattice? All right, so to answer that question, we have this idea of the geometric notion of a lattice, and we have the computational notion of a lattice. And I want to just at a high level express that cryptanalytic problems can often be solved by studying this lattice and studying the geometric properties of this lattice. There are a few different ways this comes up. For example, one of them is if you can find a particularly short vector in the lattice, then you've solved your cryptanalytic problem. There are other ones where if you can find a point in the lattice that's nearby to another point in space, that also solves the problem. And our ability to solve these problems depends on the quality of the basis. So as an example of this, here we have a different lattice basis that generates a different lattice. And we have this green disk in the middle of space. So the question is there a way to take integer sums of these two vectors to reach a point somewhere inside the circle? Now, if we had a single point, then it would be possible to solve this by just taking a matrix inverse. But when we have this circular region in space, the problem becomes a lot more difficult. And just visually, it should be difficult because as we subtract one of the vectors to get closer to the green circle, we get further away in a different dimension. And as we add in the other vector to get closer again to the circle, we move back in the other dimension. So the closer we get to the vector in one direction, one step forward is sort of one step backward. So it's unclear whether or not there's a vector within the green circle. Now, if we take the exact same lattice, but we just use a different basis representation, now hopefully this problem is easier to solve. Now the two vectors are orthogonal and they're a manageable length. So we can easily tell now that if we take multiple copies of this one in the positive or negative direction, we will never end up at a point that can reach this green circle. So answering the question of whether or not there's a point in this green circle is easy with this basis, but hard with the other basis. So that's sort of the intuition for a good basis and a bad basis, respectively. All right, and this is just depicting the points of the lattice itself. But you may wonder, what is a more formal notion of a good basis and a bad basis? And we formalize this through Gram-Schmidt orthogonalization, where we're looking at the orthogonal components of the different vectors. So here's the bad basis from before. We have the first vector b1 here on the horizontal axis. And then for the second vector b2, we look at its perpendicular component, so its vertical component, taken orthogonal to this first vector. Then we take these two orthogonal vectors and take their log.
Right, we can't hear you. Yeah. Oh. You're there. People cannot hear you. You cannot see the chat. Yeah. If you can hear us, maybe you can log out and log in again.
You were there. We cannot hear you. Your screen maybe is frozen.
I think everything is frozen. So you cannot even see the
Yeah, if you have a network issue.
yeah.
Everybody else, can you hear us?
Yes.
Okay, so probably our speaker has maybe have some connection issues.
Yeah, unfortunately, he did mention that he has some issues before, so.
Let's give him time to get back.
We can post it.
Hi, Keegan, are you back? Hi.
Hey, am I back?
Yes, you're back.
Yeah, I don't know what happened. I think I was dropped from the meeting. The Wi-Fi here is pretty bad. So what point did I drop off at?
Can you share your screen? Yeah.
Yeah.
Yeah, here. Next slide. Next slide. Yeah, here.
Here?
The previous slide.
Here.
Mm-hmm.
Okay. Did I get all the way through it, or was it near the beginning?
I think it was at the beginning, right?
Okay. Well, it's good that we didn't miss too much. I will frequently check back to make sure that my Wi-Fi doesn't drop me again.
Mm-hmm.
All right, sorry about that. So to explain this image again, so we have this process of Gram-Schmidt orthogonalization that looks at the different orthogonal components of this basis. So we have B1 on the horizontal axis here, and we have B2 on the vertical axis. B2, where we're looking at the component on the vertical axis. We can take these two orthogonal vectors and we can plot their lengths, or more specifically, their log lengths. And we can see that B1 star has a significantly longer length than B2 star, that second orthogonal component. So that gives us this large decrease when looking at the log lengths. So I'll also say that the Gram-Schmidt orthogonalization, or these Gram-Schmidt components, is actually computed in practice during lattice reduction algorithms. Actually getting these orthogonal components is an important part of these algorithms. So this is a bad basis, and you'll note that there's this large decrease between the lengths of the Gram-Schmidt vectors. To look at our other basis here and look at the different orthogonal components, we see that these two basis vectors are already essentially orthogonal. So the lengths of the orthogonal components of the vectors are close to the lengths of the vectors themselves. And if we plot them out, we'll see that there is no longer this large decrease in the log lengths of these orthogonal vectors. There is only a small decrease or a small increase. As sort of a third example here, we can have the two vectors be different lengths, where we have the first vector is small and the second vector is long, but it is orthogonal to the first vector. So the orthogonal component of the second vector is as long as the second vector itself. So now if we plot out the log lengths, we have this large increase in the log lengths of these Gram-Schmidt vectors. So large decrease is a sign of a bad basis, but a small decrease or a large increase is completely fine. Now, this has just been a two-dimensional example, but we can easily generalize this to multiple dimensions. So in n dimensions, where we have a rank n lattice with n linearly independent vectors in the basis, we can do this Gram-Schmidt process to dimension n, get n orthogonal vectors, plot the log lengths of these n vectors, and then we'll have this diagram with n different bars in it. Now, instead of depicting them as bars, we just draw them as lines for simplicity, do a line graph. So when you see profiles depicted in future slides with a line, that's essentially where it's coming from. We're taking the lengths of the orthogonal components from the Gram-Schmidt orthogonalization process. All right, so I'll pause for questions again. Are there any questions so far with good bases, bad bases? All right, so I'll keep going. So there's different ways to formalize this notion of a good basis and a bad basis. And the original one is from, that's most related to what we're talking about, is the Lovász condition. So for the Lovász condition, we're looking at the difference between these neighboring log lengths. And the exact value and the exact reason why it's this value isn't super important, but feel free to ask if you're curious. But essentially what this equation also says is that large decreases between these subsequent values are problematic and are disallowed by the Lovász condition. But small decreases, smaller than bound of 0.21, are fine, and large increases, which gives you a large negative number on the left-hand side, are also fine. So a lattice reduction algorithm takes this bad basis that does violate this Lovász condition and does have these large decreases in the profile, and it manipulates it to get a basis for the same lattice that has the same geometric properties but now has good qualities that allow us to solve the cryptanalytic problem. So that's what we want to accomplish with lattice reduction. As a few more examples of lattice profiles and what appears in cryptography, in cryptanalysis, we have this image from our paper. So we have 12 different cryptanalytic problems that can be solved using lattices for certain parameter sizes. And you'll see that each of these problems has a pair of lattice profiles, the input and the output, where the input is the profile of the basis that is the bad basis, that's the input to lattice reduction, and the output, which is the profile of the basis after lattice reduction. So if you look at any one of these problems, the image on the left typically has a large decrease, and the image on the right no longer has large decreases, but it has small decreases or large increases. And also note the scale of the y-axis can vary significantly between each of the images. So that's yeah, so the notion of exactly how large of a decrease is allowed is one of the parameters of the algorithm. So any questions about these different cryptanalytic problems and their profiles?
What is the intro-like one?
So entry-like is a lattice type specific to FPLL. So FPLL includes a program that allows you to generate different lattices, and one of the types that you can generate is called ntrue-like. So ntrue-like lattices are not generated in the same way as ntrue lattices, where you take a polynomial with small coefficients and you invert it. So what ntrue-like does is it generates a polynomial and then it just manipulates one of the coefficients so that there is a single short vector in that is spanned in the ring of polynomials using this polynomial. So it's essentially a lattice basis that's constructed to have properties somewhat similar to ntrue bases, but done using a shortcut that prevents you from having the full structure of an ntrue lattice basis.
Okay.
All right. Yeah, and I think our work is the first to sort of point out the importance of this distinction, how that shortcut of that method does matter for lattice reduction and does give different performance. All right, so those are input and output bases for lattice reduction. And sort of the first algorithm that I want to talk about is the LLL algorithm from 1982, which solves this problem in polynomial time, and it achieves a low-Voss reduced basis. So if we start at the beginning here, we'll see we have the profile, and throughout the reduction, we have this large decrease here. The LLL reduction algorithm will look at the two vectors surrounding that large decrease in the profile and locally manipulate them to remove that large decrease. And then that may introduce a large decrease somewhere else in the profile. So the algorithm iterates until there are no longer large decreases in the profile. And you'll see that at the very end, there's only small decreases or large increases in this resulting profile. So this algorithm is polynomial time. It solves our problem. So what is the issue here? How can we actually improve this polynomial time algorithm? Well, polynomial time for this algorithm is quite large and quite expensive. So even using fast integer arithmetic, we have n to the fifth, where n is the dimension, and p squared, where p is the number of bits required to represent each entry in the basis. This makes it hard to reduce bases larger than dimension around 20, which limits the types of cryptanalytic problems we can try to solve. The reason the LLL algorithm is so expensive is because computing this Gram-Schmidt orthogonalization and the orthogonal components is an expensive process. So we have to update the Gram-Schmidt orthogonalization quite a few times, and it's expensive to update the GSO. And the size of the numbers that we need to maintain in the Gram-Schmidt orthogonalization is also quite large. So the way that we speed up the lattice reduction algorithm is we tackle these two different ideas of the cost of updating the Gram-Schmidt orthogonalization by reducing First, the number of operations used to update it, and second, the precision of the numbers in the graduate orthogonalization. And so throughout this talk, I'll explain both of these approaches and explain why these two approaches are in conflict with one another. All right, so the first one for recursion, I'll just go over in a high level because the precision is more interesting. And I'll just be a little bit loose with the mathematical definitions. So I apologize for some of the informality. But essentially, the graduate orthogonalization gives us this upper triangular structure. And this upper triangular structure allows us to describe projected sublattices, which are a type of lattice where they are projected orthogonal to a few different basis vectors. So for the computational perspective, we have this upper triangular representation. And if we take a block matrix along the diagonal, this block matrix represents the basis of a projected sublattice. We can apply lattice reduction to this smaller dimension sublattice, and we can use the results of this reduction to update the larger graduate orthogonalization. So because we're doing these operations in smaller direct dimension, this reduces the asymptotic costs and the asymptotic reliance, the dependence on the dimension n. So you'll see that for the NS16, which is Neumann-Chalet algorithm from 2016, we've reduced the costs from n to the 5th plus epsilon to n to the 4th plus epsilon. And this algorithm has the best proven running time for lattice reduction algorithms. The way this happens is that the number of arithmetic operations to update this Gram-Schmidt orthogonalization is decreased, but the bit size of entries in the Gram-Schmidt orthogonalization is the same as it was before. So another note for this is this algorithm may not satisfy the Lovász condition, but it does return a short vector. So that's a brief overview for the recursive approach. Sort of pictorially and intuitively, what you should take away is that if we have this profile on the left as input, we can look at the projected sublattice that starts at vector 50 and ends at vector 151, which gives us a projected sublattice of dimension 100. We can apply lattice reduction to this sublattice or the subprofile. And after lattice reduction, this profile is flattened out. So there are no longer large decreases. There's only small decreases or large increases. So when you see the profile image where there's a subset that has been flattened out to remove the large decreases, but there may be large decreases on either side, this is a sign of the recursive approach and the acceleration that comes from using this recursive approach. All right, so that's a very high level approach, description of the recursive approach, but we can also talk about the precision management. And the idea behind the precision management is intuitive. We have the entries in the Gram-Schmidt orthogonalization are quite large. They're on the order of the dimension times the input precision. So what if we just use lower precision to represent these values? This leads us to the question of how much precision is actually needed to do so. So to take an example from before, we have this basis for a lattice, and we have this computational representation. And as we compute the Gram-Schmidt orthogonalization, this is analogous to doing a rotation in n-dimensional space. So these numbers here come directly from the Gram-Schmidt orthogonalization, and they represent an exact rotation of this original lattice. So it's just a rotation, which means that all the geometric properties are maintained. So if we can answer a question about the geometric properties of this second lattice, then that'll tell us information about the geometric properties of the first lattice. But you'll notice that although this lattice has the benefit of the basis being upper triangular, which means that we can have the GSO computation implicit in this basis representation, the values used to represent this are now are now significantly larger. So we have multiple 3-digit numbers per entry here, where here we just had 2-digit and 1-digit numbers. So the natural thing to try here is to just round these values to nearby floating points. And this is what we do here. So if I just switch between these two lattices, we'll see that in the first one, the numbers are large, and in the second one, the numbers are significantly smaller, so it's cheaper to store. But the lattice points throughout the lattice move by a small amount. So even though most of the geometric properties are still there, there's still some slight difference. It's probably fine with this amount of rounding. It probably doesn't matter, but there is that small difference between the two lattices. If we take this idea even further and round these bases even more,
Oh. Can you hear us, Keegan?
even more difference in these lattice points. Further than that, and round even further, where we even lose linear independence. Sorry about this. The residential Wi-Fi here is not that great.
Yeah.
So I think I was not far into this example when, or I didn't miss too much when I last checked. So essentially the idea here is that the more that we round these Gram-Schmidt values, the more geometric information about the lattice that we lose. So where this amount of rounding is fine, if we round it further than that to make the values even smaller, that loses information. So there's sort of this crossover point where we don't want to round the values too much because we lose geometric information, but we want to round them enough to gain the asymptotic benefits of calculating using smaller values. So the first paper to provably do this for lattice reduction was the algorithm of 1-inch delay from 2009, also known as the L2 algorithm. And they observe a condition where you can round these values. So they show that it's stable to do this if you only consider the prefix of the Gram-Schmidt orthogonalization. So you compute the Gram-Schmidt orthogonalization of the first k vectors, even if you have a dimension n. And you only do it if the first k minus 1 vectors satisfy the Lovász condition, if the first k minus 1 are already lattice reduced. So if you do this and you look at the kth vector, that the difference between the k minus 1 and the k vector may have this large decrease, it may have the large increase, but they show that it's stable to do the Gram-Schmidt orthogonalization with significantly fewer bits of precision, specifically O of n bits of precision. They show that they calculate that double precision will work up to dimension around 170. And in practice, this algorithmic approach is efficient up to dimension around 300. So the algorithm of 1-inch delay has proven running time given here, which is larger than the no 1-inch delay running time from 2016. So it is slightly worse asymptotically, but it is much faster in practice. So when people use lattice reduction, for example, through SAGE to compute a reduced lattice basis, it is using this L2 algorithm under the hood to compute that basis. We see once again that even though the cost of the number of times you have to update the GSO is still large, the bit cost is smaller because the values in the Gram-Schmidt orthogonalization are smaller. So this is how the algorithm of 1-inch delay approaches this problem. And to sort of depict what's going on here, we once again have this animation of the profile. And that idea of only computing the prefix at a time is shown by you only have a certain number of values in the profile known. But as the algorithm progresses, more and more values become known until we reach the end when all the values are known. And throughout that prefix, you only ever have small decreases or some large increases. You never have large decreases because that's how the algorithm is showing stability. All right, so this makes it significantly faster in practice, and it works up to dimension 300, which if you compare it to the original LLM algorithm, which worked up to dimension 20, that's an order of magnitude better. But this idea of using limited bits of precision is sort of incompatible with recursion, because in the case of recursion, we knew what the full profile was, so we could find that large decrease in the profile and look at the set of vectors on both sides of this large decrease. But we can't do that here because the ground truth orthogonalization is only partially known. So we know that the vectors to the left, the vectors earlier in the ground truth orthogonalization, are already reduced. And we don't know anything beyond that because we're only partially computing the ground truth orthogonalization. So we can't really apply the recursive strategy on top of this precision management technique because we don't know the ground truth vectors further along in the process. And we can't apply the precision management to the recursive algorithm because we can't show that rounding is stable if we compute more ground truth orthogonalization vectors. So that's sort of the origin of this conflict, why we can't apply both at the same time in an easy way. The first paper to attempt to apply the two together was this paper from Kirshner, Espetow, and Fuchs from 2021. And they observed that the number of bits of precision depends on the vertical spread of the profile, or the distance between the maximum and minimum values in the profile. They also make this heuristic observation that the spread decreases exponentially quickly throughout the course of the reduction process. So as an example here, we have this Z-shaped basis on the left, where the spread is 200 bits because that's the difference between the maximum and the minimum. And then after the first recursive reduction that reduces these middle 100 vectors, that middle is now flattened out. And after the second and third recursive reduction that flattens out these first 100 and these last 100 vectors, we once again have this Z-shaped basis. But now the spread of the Z-shaped basis is 111 bits. So we've cut the spread roughly in half, which means the cost of which means the bits of precision that we need to use is decreased by roughly half. And this continues throughout the process, decreasing by half again and again. They show that the algorithm cost for one of these cycles is n to the omega p, where pi is the working precision, omega is the matrix multiplication constant. And then if you take this update cost and you add it up for the exponentially decreasing precision, you arrive at an overall algorithm cost of n to the omega p. So this is based on the heuristic assumption that after lattice reduction, we just have small decreases. And because of this, we have this repeated Z-shaped structure that decreases over time exponentially quickly. And to sort of animate this out, we have the Z-shaped structure through multiple iterations. And you can see that the algorithm speeds up over time, which is indicative of the number of bits of precision decreasing over time and that update costs decreasing over time. So are there any questions at this point on this algorithm? All right, so there is a problem with this reduction algorithm. Would anyone like to take a guess at what the problem might be? What flaws might exist in this this analysis or this assumption? All right, so this paper by Kirshner, Espetow, and Fuchs, they consider the case where after lattice reduction, you only have small decreases in the profile, but they neglect to analyze the case where there are large increases. So their heuristic assumption about how the profile changes over time is incorrect. An easy example for why this is if we take n true bases, and I'll just add the caveat here that this is n true for parameter sizes that are completely different from n true used for post-quantum cryptography. So this is called overstretched n true because it uses parameter sizes that are stretched beyond the point of security. So we see that the input profile here has a spread of 200 bits because that's the distance between the maximum and the minimum. But the output basis also has a spread of around 200 bits. So that means that we need 200 bits of precision for each entry in the input and 200 bits in the output. So the precision doesn't actually decrease over time. The GSO never gets less expensive to compute, so we no longer have this convergent exponential sum that gives us this nice asymptotic running time. So the running time is actually significantly higher for counterexamples such as this, and the software that they wrote to perform lattice reduction actually just crashes on this input and does this and computes this incorrectly. So yeah, so to summarize the algorithm from 2021, it does give quite nice performance on a reduced subclass of lattices. And it's able to handle lattices of dimension an order of magnitude greater than the L2 algorithm. So it can easily reduce lattices of dimension 1,000 or more. But there are many counterexamples where this algorithm from 2021 just does not work. And it is either not stable or the runtime is not guaranteed. And in our experimentation, there were many examples where the basis at some point included a large increase, and their implementation would just crash on that input. So this is something that actually shows up quite a bit in cryptanalysis, is counterexamples such as this, and counterexamples which cause problem with the previous best algorithm for lattice reduction. All right, so to solve this problem, I'll go over it in a very high level. So we have this idea of compression from this paper by Cerrucci et al. In 2014, which sort of breaks the profile down into different components where there are no decreases between the components, only large increases between these components. So to look at this example on the left side, we have this profile with 3 different components. One is up to around index 57. One is from index 58 to around 72 or 73. And then the remaining vectors are the last component. The paper from 2014 shows that these different components can be scaled independently of one another and can be scaled down to a point such that the spread of the profile, or the distance between the maximum and the minimum values of these profile values, is smaller. So I won't go into the full intuition for why this is, but essentially this compression idea from this Cerrucci paper is a way of decreasing the spread of the profile, which coincidentally means that we can decrease the number of bits of precision that we need to use to represent the lattice basis. So there are some problems with just blindly applying this technique. For one, the original application only performed this compression step once, whereas we would like to apply it repeatedly throughout the course of our algorithm. So we need to show numerical stability. And we also need to adapt this to the idea of the recursive structure. So we have new ideas in the paper about these details. I won't go into them now, but feel free to reference the paper. But now, if we compare the previous example where the 2021 algorithm required 200 bits for this second basis and therefore did not have a decrease in the number of bits throughout the course of the algorithm, we show that by considering this value that we call the drop, which is the spread of the compressed lattice, so that smaller value that we receive as a result of compression, the drop is now significantly smaller because we look at these isolated components, we look at the spread of each isolated component and add them together. So now, in the case of the previous algorithm, we would need 200 bits to represent the second image. In our algorithm, we only need 10 bits to represent this image. So the spread is large, but the drop is small. And our algorithm requires fewer bits of precision. So we can hope that over time, because we're using fewer bits of precision, we achieve better asymptotic runtime. There are some challenges to applying this and to doing the analysis of our algorithm. So you might ask the question of, can we show that the drop decreases exponentially, our new modified notion of how many bits of precision are required? And unfortunately, the answer is no. So we have counterexamples where the drop does not decrease over the course of a single round of recursive reductions. So this rules out using exclusively the drop as a notion of how long it takes to perform the algorithm for this recursive analysis. If you're familiar with lattice reduction literature, you'll know that the lattice potential is another way to show the running time of these lattice reduction algorithms. So you might ask if the change in potential is somehow proportional to the bits of precision being used and the update cost. And unfortunately, the answer here is also no. So we have a counterexample to this as well. So we can't use the precision or as a way to analyze the asymptotic cost, and we can't use the potential as a way to analyze the asymptotic cost. But we show in the paper that we can use a combination of the two to show the progression of our algorithm. Now we do need a heuristic assumption to sort of round out the very end, but this heuristic assumption has held for all of our test cases, and we're unable to come up with a counterexample to our heuristic. So it seems like a safe assumption to make for our analysis. We achieve a similar cost per update and a similar total cost as the algorithm from 2021 with some caveats. So one of the caveats being that we use heuristic assumptions, and another caveat being that these are for well-conditioned bases, as is typically found in cryptanalysis. If you consider all generic bases, then this increases the asymptotic factor by another factor of n. So we had to have n to the omega plus 1 times this term that depends on precision. But despite these drawbacks, our implementation or our asymptotic cost is analogous to the asymptotic cost of the previous best, and our implementation cost is quite small as well. So I'll just return to the prior example of the RSA factorization problem, where this is us using our actual implementation to solve this problem. And hopefully now the profile diagram makes a bit more sense. So as this progresses and we wait for it to restart, notice the recursive structure where we're looking at a subset and removing the large decreases from that subset. So now the left and the right are both reduced because there are no large decreases. And also note throughout the course of this algorithm, the time between iterations decreases, which is because fewer bits of precision are needed at each new stage of the algorithm. So the algorithm becomes faster and faster as time goes on. Are there any questions with this one?
Yeah, did you just show the first 80 dimension here in this picture? That's exactly.
Yeah, so one of the things with this RSA partial factorization problem is one of the parameters that you can tune is the size of the lattice that you're reducing and the number of bits of precision that you brute force. So as you reduce the number of bits that you brute force and thus make the brute force easier, I believe you exponentially increase the dimension of the lattice. So the reason why we show the first 80 vectors here is because we're reducing a lattice of dimension around 80 or so, because there's this trade-off between the size of the lattice that you reduce and the number of lattices that you have to reduce. So this is just one example of the trade-off that we show.
Okay, thanks.
All right, so we also have this example from before of the Gentry-Levy fully homomorphic encryption problem. And you can, again, here see the recursive structure in action. So we're looking at the first half of the vectors and reducing that first half. Now looking at the middle, reducing the middle, and so on until the whole thing eliminates the large drops and only has a drop of size that we will allow. All right, there are other results that we have in the paper that show that our algorithm is faster than the previous best. But just to summarize, lattice reduction is a very important tool in cryptanalysis that appears in many different settings, and the profiles of the lattice that appear in cryptanalysis are greatly varied. If you remember that that image of the 24 different profiles, there's wildly different behavior across cryptanalysis. The ways to make lattice reduction faster are both recursion and precision management, but it's difficult to combine the two. This paper from 2021 found a way to combine them, but it doesn't work for all lattices that we care about, and it only works for a small subset. So we found extending the algorithm 21 and re-analyze our implementation, our algorithm are significantly faster than existing applications and significantly faster than what you'll find in Sage for lattices that are either large dimension or have large entries. And we conjecture some future work about how we can make this algorithm even faster than it is now. So the preprint for this paper is online on ePrint, and we also have our code available on GitHub as well. We also, in addition to including the code for our reduction algorithm, we include the code for visualizing this profile. So if you have a problem that requires lattice reduction and you're curious about what is going on with the profile and how it behaves over time, and maybe using that to give more insight into the structure of the lattice, we also have that visualization tool available online as well. So with that, I'm happy to take any questions you have, and thank you for your attention.
Keegan, are there any questions? Yes.
So, in your slides, in the very first, in the beginning of the slides, you mentioned some certain problems, like the N2 and the Alchais.
Yeah.
This one. So this one, how did you make the, you generate the random lattice and then you use the LLR reduction for the every lattice?
Yep. Yeah. So basically, we went through the literature and found the examples where people are using lattice reduction. For these examples, yeah, we went through the papers and constructed examples according to the paper. And then I think for these examples, we did use that the L2 algorithm from 2009 to compute these reduced bases. So these are actual examples for the schemes in the literature and actual examples of their cryptanalysis.
So same problem and same algorithm you used, right? I mean, the different problems, same algorithm for all the problems.
Yep. Yeah. So essentially, for these different cryptanalyses, the type of cryptanalysis will determine how you construct your lattice, and how you construct it will change the input. But then once you have that input lattice basis, then it's just the same algorithm applied on top of that. So it's a single lattice reduction algorithm that takes that basis and transforms it into this reduced basis. Then what you do with that reduced basis does depend on the algorithm, because these different, or it does depend on the cryptanalysis, because the different cryptanalyses will look for different properties in this reduced basis. But sort of that middle step of performing lattice reduction is exactly the same for all of these examples.
So the parameters is for the every problem is same, or the how did you deviate the parameters? Because different problems has different parameters to compare.
Yeah, so ntrue, which is right here on the left. So ntrue is parameterized by a few different things. One of them is the dimension that the ntrue problem is in. Another one is the size of the modulus. And there's also things like the distribution that you draw your function from. So the way that corresponds to the lattice that you construct is the dimension of the lattice is twice the dimension of the space in the ntrue problem. and the spread here. So we have the values 0 and 60. This is because we're using a modulus of size around 2 to the 60. So some of these parameters for the intro problem are solvable using lattice reduction. So this set of parameters that we've chosen here is solvable, and other parameters are not solvable using lattice reduction. So ntrue, as is used for post-quantum cryptography, uses a different set of parameters where the modulus is much smaller, and you have a different behavior in the lattice reduction algorithm. So that's sort of where the different parameters for ntrue comes into play. Is we look at a subset of the parameter space where it is solvable using lattice reduction, whereas the parameters used for post-quantum cryptography are selected such that lattice reduction does not apply. So that's sort of the distinction for ntrue.
The adjustment, the sixth problem you used in here, the second.
This I-type problem here.
Yes.
Yeah, so that is another type of profile that's supported by FPLL and is used to sort of benchmark the performance of lattice reduction algorithms. I think it originally came up in the context of hash functions, although there aren't any applications that use this type of I-type lattice now beyond profiling or beyond benchmarking lattice reduction algorithms. So that is sort of a, it's a basis where the size of the values on the diagonal are exponentially increasing, and the other values are randomly chosen.
Okay, thank you, Ryan.
Yeah.
Thank you very much.
Are there other questions that I can answer?
If there are no questions, or are there any questions? If not, let's thank Keegan again. Thank you very much.
All right, thank you. And thank you for bearing with me for all the technical issues that we had.
That's not a problem at all. Okay, thank you.
All right, thank you. All right,
Bye.
have a good day, everyone.
Bye.